Go ahead.
For the partial derivative t of x, we made a secant line going from 4 to 8. Going from 4 to 8 for the x.
Okay. Going from 4 to 8 along the x. Okay, I gotcha. Yep.
And then we found like the slope of that secant line.
Yeah. Okay, so tell me if this arithmetic is right. Did you do 86 minus 72 divided by 4?
Yeah.
Is that right? Good, because what he's doing is he's keeping y stationary and he's changing x, right? So 86 minus 72 is what? 14 over 4. So we get an answer of 7 over 2 or 3.5. I think that works. That's at least what the text said to do. That's good. Another way that they say in their solutions, hang on one sec, is to average the two lines that are like from say like 4 to 6 and then from 6 to 8, but it gets us our same answer. Good. So I'm going to ask someone else. Hang on one sec. Max, what would be the units on this? Any idea?
No.
Okay, what's big T? It's measuring temp. And then what are we doing as far as moving around? We're in meters. So this would be degrees Celsius per meter. Go ahead.
Why wouldn't you use an adjacent point and the point itself? Like, why are you using the 2 points surrounding?
Well, this works in the same way that averaging the two also works.
Yeah, but like,
So
in my mind, it's like when you take a derivative, what you're doing is you're taking the point,
yeah.
and then that point that's h over,
Yeah.
and then you just find the secant line, it's h gets small,
Mm-hmm.
right? So you're using the point and the adjacent point. Isn't that like better because you're closer? Like you're not choosing 2.
But you're still going to have to choose 2 adjacent points here because just doing one of them only gives us a sense of what happens on one side of the x value. We would also want to know what happens on the other side of the x value.
But that's actually the way the solution manual does it, is they say, let's find this. Let's find t of 6,4 minus t of 4,4 all over 2. And let me show you what this is. This is 80 minus 72 over 2, which is 4. And then they do it again going the other direction, right? So they say, no, not the other direction, but further. They say, so let's go to t of 8 comma 4 minus t of 6 comma 4 all over 2 again. And that is 86 minus 80 over 2, which is 3. And so then they just say, let's average those two. And that gets us the same answer that Sanjeev did. So I say this is probably valid. I don't see anything wrong with that. Okay. All right. That was A. Very good. Oh, no, that was part of A, wasn't it? All right. Let's pick someone else. Nick, can you walk me through the other part of A? T sub y at 6,4? Yeah. 75 minus 80 divided by, wait. Let's see if this method works the same way though. Like if I average the two. So let me try it this way first. It does work? Okay, fine. We'll just do it that way then. Yeah, so 75 minus 87 over 4. So what's that? Negative 12 over 4, so negative 3. Is that what you got? Okay, so this is t sub y at 6,4. Okay, cool. All right, so we've got A done. B, question? No? Other questions? Anything we need? Have we gotten to B yet? Yes. Okay, let's talk through it. Okay, if you haven't gotten to B and I call on you, I'll pass it off to somebody else. So it says, estimate the value of d sub u of t at 6,4, where u is the vector 1 over root 2, 1 over root 2. Well, what's nice is that we really know gradient t, don't we? Gradient t at that point is 3.5 comma negative 3. So I'll talk to Jaron. What do we need to do with gradient t and u in order to get dot them? Exactly. So we're just going to take 3.5 times 1 over root 2 plus negative 3 times 1 over root 2. This is our answer, and I don't really care what the value is. Cool? It's not quite 0. It's near 0. Okay, C. Estimate the value of t sub xy at 6, 4. Has anyone made it to that? Spend a little time. Spend a little time on this, and we'll talk in a minute, okay? Here, 1 sec. Okay, guys, focus up here, please. Or at least stop talking. Go ahead. 8 times.
8 times 5y cubed plus 2x squared times y.
Uh-huh.
Also 7.
Good.
Times 4xy.
4xy, perfect. Because chain rule tells us the derivative of this thing now is that thing goes to 0 and this thing becomes 4xy. Nicely done. Can you also do the partial with respect to y?
Yeah. It would also be.
Same deal, right?
Yeah.
Yeah. And then our other term would be what?
15y squared plus 2x squared.
Plus 2x squared. Nice. Good. All right, let's pick one of the rest of those to do that maybe looks a little more challenging. Let's try 16, please, okay? Everybody do 16 right now. G of xyz equals e to the xz times the sine of y over z. I want 3 partials, please. I want you to do del g del x, del g del y, and del g del z. Try those now, please. Sorry, I wasn't ready to write. Can you say that again? I like it. Y over z. Yeah, right? Because if we're differentiating with respect to x, this whole thing is a constant. And so it's really just a constant times e to something. So you did e to that something. The derivative of that something is z, and then times the constant that's sine of y over z. Good. All right, let's take someone else for del g del y. Nathan Wong. E to the xz over y. Yes, I like it. Okay. All right, so e to the xz over y, because he's recognizing that this thing is a constant if we're differentiating with respect to y. The cosine of y over z times the inner derivative of this is his, that's where he gets the 1 over, wait. 1 over c, right?
Yeah.
Did you say that, or I may have written it down, Nathan, I'm sorry. He probably said it right, I'm sorry. So, cosine of y over z. Okay, and then the last one. Josh Sorkin, can you give us the partial of g with respect to z?
Yeah, it's x times e to the xc times sine of y over z.
Okay.
Plus e to the xc times cosine y over z times negative y over z squared.
Oops, negative y over z squared. All right, let's check them on that. Okay, so use the product rule. The derivative of the first thing is x e to the xc times the second thing. And then we've got the first function times the derivative of the second, which I agree with. Nice. Good, so both of these required nothing fancy because some convenient stuff was constant. This one required us to do the product rule. Okay. Let's do one more decent, solid problem that takes you a little time, and then we'll move on to the lesson for today. Let's have us try. Can you look at 37, please? Look at 37. Okay, everyone. Here is the goal, and here's how we're going to do it. Let's come back together and start these, okay? So the goal is to find both absolute and local maxes and mins, okay? So we're going to find absolute and local maxes and mins of a function of 2 variables, right? Of f of x, y. You may remember the lesson on this from single variable. Let's just kind of think about that a little bit. If you wanted to find absolute max and mins of f of x, you would find f at the endpoint, f at the other endpoint, and then analyze any critical points. Okay, so absolute max and mins. If you wanted to do local maxes and mins, you'd use the second derivatives test. You'd say you find a critical point, and then if second derivative is positive or negative, that would help you know what's going on. Okay? In order to do that, we're going to use what's called the second derivatives test. And we're going to use the second derivatives test to classify the extrema. And you'll see that word in our text, the extrema, that just means maxes and mins or critical points. So the second derivatives test to classify, and they're going to just be a local max, a local min, or a saddle. And there is a case where the test that we use is inconclusive, but that just means you would need to use a graph or some other means to understand what's going on there. Okay, so we'll start with a theorem to talk about how we find these critical points and where these maxes and mins occur, and then we'll dive into actually this test. So if f has a local max or min at AB, and the first order partial derivatives of f exist there, then f sub x at that point equals 0, and f sub y at that point equals 0. Notice what this is not saying. This is not saying that if both partials equal 0, then you have a max or min. The converse of the theorem doesn't necessarily hold, but the forward direction of the theorem holds. If you have a max or min, this is going to happen. Okay? So what we're looking for is we're essentially looking for horizontal tangent planes. When we're looking for maxes and mins, we're not looking for a horizontal tangent line, but a plane, like that's been the case in so much we've done this year. Okay, so we're going to be testing critical points of the function. Where do those occur? So the definition of a critical point. The point AB is a critical point of f if one of the following is true. One is that f sub x at AB equals 0 and f sub y at AB equals 0. Notice the statement and. It can't just be one of them. They both have to be 0. In other words, you guys were discussing this earlier at that table, the gradient is 0, right? If the partial with respect to x and y are both 0, this means that nabla f equals 0. Just maybe put that in parentheses. That means that nabla f is the 0 vector. So critical points occur then. The other condition where they occur is if one of them does not exist. So if f sub x at AB or f sub y at AB does not exist, or they're undefined at a point, then we don't actually encounter that much in practical problems, but if one of the other or the other doesn't exist, then we also have a critical point. Okay, so we might discover critical points which are neither a relative min or max, and that's where we should be thinking about the Pringle, right? The saddle. So that's what's happening when that happens. Saddle / Pringle. A Pringle is much more tasty than a saddle, I assume. What are saddles made of? Leather? Yeah, that would be gross to eat. Okay, so here's a function. As our first example, we have a function. We're going to find the critical points and determine whether they are local max, local min, or neither. Now, we don't know the second partials test yet. So once we find the critical point, we'll have to use some other means, graphing or something to determine it. All right, so f sub x. Let's call on you guys again. Jacob, what's f sub x of this function, the partial with respect to x?
2x minus 2.
2x minus 2. Good. Nice, easy. Eric is not here. Matt, what's f sub y? 2y minus 6. Good. So if we want to find the critical points, we're going to set both of those equal to 0. That's pretty easy. We don't even have a system to solve. This leads to x being 1, and this leads to y being 3. So our only critical point here is 1, 3. Now, eventually we'll learn about how to test this point using the second partials test. We'll get to that in just a second. But for now, if you don't have that, we just need to think about the structure of this. And you might recognize this as a paraboloid, right? So I'm going to complete the square on it, and we'll kind of reveal what's happening at that point. So we've got x squared minus 2x plus 1 plus y squared minus 6y plus 9 plus 14 plus, -9, and -1, right? We have to make those adjustments on the end because we did this earlier. So this function turns into x minus 1 squared plus y minus 3 squared plus 13. No, plus 4. Thank you. And so we see that this point that we've identified as the critical point is actually just the vertex of our paraboloid, right? So it's the point 1, 3, 4. That is the vertex of an upward opening paraboloid. So therefore, it is a local, well, actually, and an absolute, but local / absolute min. So, right, because the lowest this will ever be a 0 and the lowest this will ever be a 0, we know that 4 is the lowest z value ever on this function. But they don't all work out so nicely, so we need a test to determine when that doesn't happen. Questions so far? So just to review, key to finding critical points, set the partials equal to 0. Sometimes it's a difficult system. Sometimes it's really easy linear equations like this. Okay, so in this case, we already know what the thing's going to look like. Let's see what happens when we try and find critical points. So f sub x is negative 2x. F sub y is 2y. And when we set this equal to 0 and this equal to 0, we know that the only critical point is that x and y both equal to 0, which is right there. But what we see is that along this path, I'll use dashed line to go on the bottom there. Along that path, we have a local max. But along the other path, we have a local min. And this, of course, is the situation where we have the saddle. That's the classic graph, the hyperbolic paraboloid where that happens. And we're going to see what happens in the partials test when that's the case. Basically, at this point, the two partial derivatives are not going to agree in sign or something along those lines. There's a nice proof of the whole thing. We should probably explore the proof once we write it, but it's not. Don't require you to understand all the steps of the proof. So that's just an example where the critical point is not a max or a min, right? It's going to be a point where along two paths, it's a different thing. So here's the test, and then we'll go look at the proof and see if we can understand any of it. I've glanced at it in the past, but we don't ever dive into actually showing it. So let f have continuous second partial derivatives on an open region containing the point AB. So it's just saying we're near AB, and second partial derivatives are defined and okay near that point. Okay, and we have a critical point, right? If f sub x is 0 and f sub y equals 0. So we can just note that we're testing this at a critical point. Okay. Oh, I wrote that right there. Dumb. Okay, so thus AB is a critical point. So to test for relative extrema of f, we consider this quantity. It's commonly known as, well, at least our text just calls it capital D, and it's f sub x at AB. Sorry, f sub xx times f sub y at AB minus f sub xy at AB squared. Oh, shoot, there should be two y's there. I'm sorry. I think I wrote that. My pen just didn't pick it up. fxx, fyy, fxy. I don't remember my vector calculus from college as well as I want. Are some of you familiar with the Hessian matrix? Noah? No? Nathan? Any other math teamers? The Hessian matrix? Okay.
I totally.
Okay, check it out. Look at what this is. This is the large, like, n by n case, but look what's in it. You've got okay, so you've got
the second derivative of f with respect to the first variable twice here. Just pretend this is a 2x2 case. The second derivative of f with respect to the other variable twice, so that's on that diagonal. Then these diagonal have those mixed partials, f sub xy and f sub xy. So this thing right here is the Hessian matrix, and guess what our d value is? It's the determinant of the Hessian matrix. Okay? So I don't remember all the properties of this, but maybe they give a little info here. It's symmetric. Yeah, it talks about the Jacobian matrix. We'll learn about that later. I didn't know this. It's the Jacobian of the gradient. That's interesting. So here, right here. Here you go. It even talks about what we're studying right now. The Hessian matrix of a convex function is positive. I don't know what that means. Here. Refining this property allows us to test whether a critical point is a max, min, or saddle as follows. So if the Hessian is positive, definite, I'm going to put all this language in stuff we can understand, okay, basically. But the Hessian matrix, the determinant of the Hessian matrix, is what we're examining with D, okay? So here are the conditions. Part one option is that D is positive, and f sub xx is positive. Under those conditions, then we have a local min. Okay, so the determinant of the Hessian, this thing here is positive, and fxx is positive. Think of that as like concave up, okay? Then we have a local min. The other option is when D is sorry, not that one yet. When D is positive and fxx is negative, then we have a local max. So think of that as, think of this component as saying like downward concavity, right? So we're at a max. The third condition is what if D is less than 0? And then we have a saddle. Ooh, I bet Trefor has a nice video explaining this derivation. I will search for it. I will watch it tomorrow and get back to you. And then 4, what happens if D equals 0? Then unfortunately the test is inconclusive. And that just means that it might be one of the others, but the Hessian is not revealing it. This matrix is not revealing the information. Okay? So let's take a peek at the proof and just see if there's anything there that sheds any light on this for us. I don't expect you to understand the proof, but why not have a look? All right, so hang on a second. Yeah, you can, is it in the appendix or is it in the actual section, Noah? Whoa, careful, my boy. Don't fall down. Here it is. So you guys, all they're telling us, this proof, let me make that a little larger so we can see better. This proof is only showing us the first part of the theorem. It's only showing us about the part where we get, I believe, a local min. I don't know, let's read it. So we compute the second order directional derivative of f in the direction of u equals hk. The first order derivative is given by theorem 14.6.3. Okay, that's no big deal. We know this. It's the gradient dotted with a unit vector. That's the directional derivative. So applying this theorem a second time, we have that the second order directional derivative is the derivative of the first order, which is the first component of the gradient of the first directional and the other one. Okay, that's fine. And so how do they go from there to there? Does that make sense to us? Oh, sure it does, because look what we're dealing with. So at first we had fx and fy. Well, now we're just doing that again. fxx and fxx. I don't know, that doesn't make sense to me.
You're acting with respect. You're taking the top derivative with respect.
Oh, yeah. Good job. Thank you. Yeah, that's right. We're taking the top derivative with respect to x and then the top derivative with respect to y. Good. So what does this give us then? Fxx h squared plus that plus fyy. Okay, so they're just cleaning that up a little bit with algebra, or no? By Clairaut's theorem. Do you remember that?
Oh, yeah.
These two guys are the same, right? Fyx and fxy. Okay, then they say we complete the square in this expression, we obtain. Okay.
The second directional derivative.
I don't follow this stuff. Okay, maybe that's where my understanding is going to break down. And then there's a whole paragraph. Oh boy. I bet you that Trefor has a better explanation. Let's check out what he says. We won't watch it, but well, it's 13 minutes. I'm gonna watch it tomorrow, okay? It's going on my to-do list. Trefor second partials test. Yeah, we'll watch it during math team. Good idea. I like that idea. Back to the textbook. Oh, you're going to try and understand this right now? How about this, my friend? I'll email it to you and you can play around with it. I'm going to finish the lesson. Who? I can never tell who's speaking with the masks on. Yes, of course. Yeah, who's Joe? He's in my class. Who's that guy? Okay, there you go. Oh, I was videoing that whole thing. That's awkward. You want it too? Sure. Okay, let's try this one now. Find the extrema and find what they are. You think you can do it on your own? I bet, well, is there another example I could have you do on your own? No. Okay, I want you to try it, please, okay? I want you to find the critical points. All right, so I want you to find the critical points, and then I want you to classify them. Are they maxes, mins, or saddles given the second partials test, okay? Spend a little time, and I'll send the proof to Lucas who wanted it. Okay, I am re-recording. Let me explain my work, please. Critical point, 0, 0, and 4/3, 4/3. Let me just walk through a little bit of that solving process so you understand it. Right here, this is the equation I use to establish that x equals y, right? Because if 4x equals 4y, I can divide to get x equals y. Then substitute that into this equation so I have one equation with one unknown. So I have something that's factorable and I lead myself to here. Now remember, we're talking about points in the xy plane where that's happening. So this really means the critical point is 0, 0, and this means the critical point is 4/3, 4/3, okay? So be comfortable with doing this kind of stuff because I can't really let you have your calculator on this if I'm testing you on taking derivatives. I don't want you to be able to just do that. So those are the critical points. And then I found D at 0, 0. So in order to do that, I found each of my second order partials and computed D to be -16. So this point is a saddle. Technically, I guess I should say 0, 0, comma, whatever it is there, 0, 0, 1, but whatever. Yes?
What do you mean it's saddle?
That means that along one path, it's a local min, but along another path, it's a local max. We'll go explore the graph in just a second and see it. Okay? You can see my same work here, getting me 16. Okay? Let's look at the graph just for the sake of interest. All right. Okay, so it's z equals -x to the third plus 4 times x times y minus 2y squared plus 1. Okay, quiet down, guys. Let's look at this together. I'm going to add 2 points to it, okay? First is going to be the point 0, 0, 1. And this should be at a location where we see a saddle. Let's see if we can find it. Right there. See? Because along this path, it's a max, but along this path, it's a min. So that's our first critical point. What is 4/3, 4/3? Do you know the z coordinate there? Let's figure it out together. Okay. So negative 4/3 cubed plus 4 times 4/3 times 4/3 minus 2 times 4/3 squared plus 1. So it's 59/27. Okay. So we're talking about the point 4/3, 4/3, 59/27. Okay, let's use a pink color for that one. So you can see let's make it bigger. 10. There we go. Nice big point. Okay, that point right there then is what we expected from our second partials test. It's a local maximum, right? And so that's what the graph looks like. I don't know if anything else interesting happens as you zoom out, but so it's got kind of this like cubic look along one route. So let's tackle this and see how far we can get. All right. That was all about local max and mins. Let's do absolute. Here's how we do it. To find the absolute max and min values of a continuous function f on a closed bounded set. Okay, closed bounded set. That means that like we're going to have some boundary, right? There's going to be some curve that bounds us out. Thankfully, the curve's not going to be complicated like that. It's often just going to look like a rectangle. Like you've got a curve that's, kind of taking us around that rectangle, and that's the boundary. Remember, in single variable calc, your boundary was just on the x-axis, right? So that was really simple. Now it's going to be bounded by some curve. So this would be the set D. That would be the set D there. All right, so here's the action steps. Number 1, find and test the critical points. That's part 1. Same deal as before. That's what we've been doing all day. Find and test the critical points. Okay. I know. Mr. Sutherland's really going on that board. Okay. Step 2, we are going to examine, that's probably the best way to say it, examine each boundary and the endpoints of those boundaries. Okay, and when I say examine, I mean we're going to like actually see what happens to the surface along that boundary, and then we're going to do some single variable work. Okay, so why don't we put it this way? Make f of x and do single variable calculus. You'll understand when you see an example. Okay, because what's going to happen is I'm going to say, hey, if we're going to travel along this boundary, f of xy is just going to turn into f of x0. So we're going to have a much simpler function to work with. And then basically the moral of the story, the whole thing was trying to find a max or min. So step 3 is just take the highest and lowest values of everything you find. And those are your max and your min. So in single variable calc, it was a matter of, you have a function that's doing this, and I want to know between here and here, right? You're going to need to check critical points, and you're going to need to check endpoints. In multivariable, it's check critical points and the whole boundary of your domain. Okay? They're kind of cool problems, actually. So let's try this one. It's a little bit of a beast, but we'll get through as much of it as we can. Okay, let's draw it first so we have a reference for what we're doing. We're going 0 to 3 and 0 to 2. This is our rectangle. This is our region D. And we want to talk about what is happening to this function on that interval, on that region. In other words, what's the highest and lowest points it takes on that region? All right, so first let's analyze critical points. F sub x is 2x minus 2y. And f sub y is negative 2x plus 2.
Okay, that's convenient because this leads us to x equal 1. We don't really have to solve a system, do we? When we set the top thing equal to 0, that means that y must also equal 1. So that leads us to y equals 1. So our critical point is 1, 1. And when I say find it and test it, I mean sub that point into the function to see what value it takes on. So we've just found this point right there. I'm going to put a little check mark that we've just found it so we can kind of keep track of what we've done. So what is f of 1, 1? 1 minus 2 plus 2? So it's 1.
1, 1.
It's 1, 1, 1. There you go. All right, so the function it takes on a value of 1 at the critical point. Okay, now, in a case like this, it will be wise for us to just check all of our endpoints of our boundaries real quick because it's all nicely laid out in a square. But some things won't have boundaries like that. They won't have corners, so you'd just be checking the boundary itself. So let's do that. Let's check f of 0, 0. What is it? 0. Put a box around it because that is a candidate for being the highest or lowest once we get to the end. We're going to get to the end and then say what's the highest, what's the lowest. So I'm going to put a dot here and put a check mark to acknowledge we've checked that spot. Let's check f of 0, 2. What's that? 4, yes. 4. So let's put a check mark here. So I'm just going around. Let's go f of 3, 2. 9 minus 12, negative 3 plus 4. Is it 1? Thanks. Okay, so we've checked this point. And then f of 3, 0. Yeah, 9. Good. Okay, so far, the winner is 3, 0, giving us our maximum, and the loser is 0, 0, giving us our minimum. That feels mean to call it a loser, but whatever. Okay, so great. There are corners, so we've checked the corners. Now we have to do single variable calc on all of these boundary lines. Okay? So it'll go quickly because the functions end up being very simple. Okay? So let's start first with the left side. So along the path x equals 0, while y varies from 0 to 2, we've already thankfully checked the endpoints. We did that already in that thing checking the corners. But let's now figure out what this function becomes. F of xy is no longer a function of x and y, but rather just a function of y. So it's the function f of x equals 2y. That's not a good way to write that, you guys. Let's put a 0 in place of x. That's a better way to say this. Can you fix that, please? F of 0y equals 2y. But this is easy. 2y is linear. It doesn't do anything interesting. So we can just say, since linear, our work is done. Okay, maybe don't be that dorky in your notes, but because we've already checked the endpoints, and clearly a linear function is going to take on its extreme values at the endpoint. So we don't have to, there's no critical points of 2y. No work necessary. Okay, let's move over to the right-hand side of the box. So let's talk about along the curve x equals 3. So the function turns into, if I sub in 3 for x, it's going to be 9 minus 6y plus 2y, or the function 9 minus 4y. What else can we say? It's linear again. Easy. No work needed. It's linear. Nothing interesting is happening there, right? Okay, now the other two, I promise, do provide something a little bit more interesting. Let's do the top one first. So along, what is it? Y equals 2 as x varies between 0 and 3. Thankfully, we've already checked the endpoints there, so we don't need to worry about that. But the function turns into this. It turns into x squared minus 4x plus 4. And that thing's not linear. So something interesting may happen on the region between 0 and 3. So what we're going to do is we're going to take f prime, just like single variable calc, we're going to find critical points of this new function that's just of a single variable, which is 2x minus 4.
And when is f prime equal to 0? When x equals 2, right? Okay, did I make any algebra mistakes? 2x minus 4, 0, 2. Okay, I think we're good. So this means that f of 2, 2 is another point that I have to test. And that point is located like right here. In other words, this is a critical point of the function that's produced along this line, you know? So let's see what it is. What is f of 2, 2? It's, oh, is it? Oh, that's boring. Okay. So, oh, but actually, that's 0 is still the loser for being the minimum, right? Or we could say the winner for being the minimum, and the other one's for the max. So this is a possibility. So far, we have tested, let me do my color matching here so it looks really pretty. Along x equals 0, we've tested this path, we have tested this path, and we have tested the path up top where you see my green check mark. So the last thing is to check when y equals 0. So let's do that. What color should we use, kids? Rainbow! That's what's going to make the day really happy. Here we go.
The galaxy?
You want the galaxy instead?
Ooh, what is galaxy?
All right, we'll go with the galaxy. Okay, so along y equals 0, as x varies from 0 to 3, let me change to galaxy. There it is. Oh, it's so beautiful. Okay.
Galaxy.
All right, so what happens now is we get the function f of x0, which is just x squared, right? Okay, well, also boring, because on the interval from 0 to 3, x squared doesn't do anything interesting. It's always increasing, which means we don't really need to check for critical points, because the critical point would just be at 0. We've already checked there. So our work is done. Okay, so what is the winner? What is the loser? The maximum is 9. Okay, so we'll say the max is 9, and it occurs at the point 3, 0. And the min is 0, and it occurs at 2 points. It occurs at 2, 2, and at 0, 0. Okay, now we're out of time, basically. Okay, that was cool that we got that far, though. That was great. We're going to practice more of these because they get a little ugly and different when they're not so straightforward like this one. But that was great that we got through it, so thank you so much. I will read your feedback carefully. I will respond to some of it next class. Thanks for whatever you wrote. And homework is posted, I think, with video solutions already as well.